Okay, so vertical line test. We know how to find out quickly and easily if any relation that's given to us in ordered pairs is a function or not. We know how to find if a table is a function or not, a mapping is a function or not, and simple graphs. We know how to find if those are a function or not. But what about continuous graphs? Okay, so if I'm looking at a continuous graph like the ones that we have on this page, it's a little more challenging because I don't have a firm, they're called discrete graphs. These are called continuous graphs. A discrete graph has several points that you can find specific x and y values. The domain and range of these is a little more unclear. We could go through the process of finding those, but we're not necessarily going to. Okay? All right, so the vertical line test is a way to determine whether or not a relation is a function. Okay, and we've learned how to find out if several different varieties of relations are functions, but this one's just going to be a little bit different. Remember that a relation is a function if, I'll give you 10 seconds to fill in the blanks with your partners for that one. Together with your partners. Requires you to talk a little bit. A relation is a function if every... Yeah, there we go. Okay, so what is it? Remember, a relation is a function if every what? Input has what? You guys are getting a little too vague for me. I can't say if every input has an output. I have to be specific. One output, right? So if every input has one output. Okay. All right, so the vertical line test simply states that if a vertical line intersects or crosses the relation's graph in more than one place, then the relation is not a function. So remember, every input has to have exactly one output for it to be a function. So let's look at this. We know that inputs are the same as what? Domain is the same as x values, right? So if I'm looking at this graph number 1, if every x value has exactly one y value when I go up and down, it is a function. That's why we call it the vertical line test. Okay, everybody show me a vertical line. Perfect. We're all geniuses at that. Okay, vertical line test. So if I have vertical lines on my graph, just like this, so I'm actually going to draw mine on here. You guys don't necessarily have to. So if I'm checking with vertical lines, I am currently checking x values, right? So if I'm checking vertical lines, I'm checking x values, and I'm checking to see does every x value have exactly one y value that goes with it. So this line that is, so everybody look up at my screen. This line right here, how many y values does this line hit? 2. 1 right here and 1 right here. That means this x value of 4 has 2 y values. That's one input with 2 different outputs. So here up in the paragraph it says, for each graph, place your pencil vertically on the paper. So obviously we don't have pencil and paper anymore, but you can put your stylus down. I don't care what you do on your screen. And slowly move your stylus or pen or finger, whatever you want to do, across the graph. If any of these vertical lines hits the graph at more than one point, that means that input has more than one output. So if yes it hits more than one point at the same time, the graph is a function or is not a function? It's not a function, right? So if it hits more than one point, the graph is not a function because that means every input has, or an input has more than one output. Okay, if no, let's look at number 2. So I start moving across with vertical lines. Do my vertical lines ever hit the graph at more than one point? No. That means every one of these inputs has exactly one output, right? Every one of these inputs has exactly one output. So if it does not touch more than 1 point at any point, then it is a function. Okay, it's as simple as that. So I want you guys to finish these 2 pages. There's 3, 4, 5, and 6. So I want you to go together with your partners, do your vertical line test, decide if they're functions or not. Go ahead. Okay, so on 3, I'm running my vertical lines across. At any point, do any of my vertical lines hit more than 1 point? No, so it is a function. Okay, what about 4? I run my vertical lines across. Looks like they're hitting the graph in one spot every single time. So again, 4 is a function. Okay, then I start going through 5 and I start chopping with my vertical lines, and it looks like several of the vertical lines hit at more than 1 point, right? It's hitting up here and down there. So if that vertical line is hitting in more than 1 point, this one is not a function. And lastly, 6. Looks like I'm hitting in 1 point the entire time. That is a function. We are currently leading into function notation. This is similar to what we did on warm-up, but on A, it gives you this function machine. I want you to make an input-output table just like we did on warm-up. So the input-output table, and you can put it over to the side if you want to. We're doing it for 5A. So I need my pen. So I'm making my input-output table. Remember, our x values are going to go here. And then the expression, what expression are we using here? What function are we using here? Brandon?
2x plus 5.
The 2x plus 5, right? That's what's in the middle of the function machine. So 2x plus 5 is the function we're using. So x is the input that we're using. 2x plus 5 is the function that we're using. And then we're going to get some y value or output value in. So A asks you to use 7, -2, and 1/2. Okay, so go ahead and make your input-output table for 7, -2, and 1/2. Make sure you're doing it with your partners. Make sure you're talking through it. Go ahead. Okay, so my input-output table, I'm plugging in these inputs. So we want to start thinking about this idea of taking inputs, taking a specific function and plugging them in and finding an output. Okay, so if I take 7 and I plug it in, I have 2 times 7 plus 5. Well, 2 times 7 is 14 plus 5 is 19. Okay, I plug in a -2, so 2 times -2 plus 5. 2 times -2 is -4, plus 5 is 1. And then I plug in a half, so 2 times a half plus 5. Well, half of 2 is 1, plus 5 more is 6. Okay, so an input-output table is a good way for us to be able to write and list out inputs with a specific function and corresponding with an output. Okay? But I think you guys can all agree we don't necessarily want to make an input-output table every single time we do a problem like this. Okay? It's not too awful bad to do this, but I mean it takes a little bit of time. So instead, we're going to use something called function notation. So go ahead and flip over to the next page. Or scroll down. Yeah, that too. Alright, so looking here. Okay, function notation. So we need to look at the terminology and what function notation looks like, because I don't want you to be intimidated by function notation. Okay? This over here, so everybody look up at my screen. This over here is what shows you you're using function notation. Okay? So there will always be, and you might want to highlight this or circle it or something like that. The letter that's out front is the name of the function. Because think about it, if we're using several different functions at the same time, it's very useful for us to be able to determine which function we're looking at, and we do that by using a name. So it's not always f. It could be f of x, g of x, h of x, any letter really you could use there. Okay. And then also the other part of the f of x, the x. X is going to be the input variable. Okay. So f is the name, x is the variable, and then this over here is the function that we're using. So you can see all in one line the specific function you're using, the input, and the output. And this 9 minus 4x is also the output. Obviously, it's not a perfect output, okay, because we haven't plugged a number in for x. But once we plug a number in for x, that will be our output. So we have inputs and outputs side by side paired with the specific function that we're actually using. Okay, so let's look at some real examples here. We're skipping 1. Let's go down to 2. So it says function notation is useful for evaluating functions for multiple input variables, values. To evaluate f of x, so again, it's read f of x, not f parenthesis x, not just fx. It's read f of x, or f of whatever number you're putting in. Okay, so to evaluate f of x equals 9 minus 4x for x equals 2, we substitute 2 in for the variable and write it f of 2 equals 9 minus 4 times 2. If we simplify it down, it gives us f of 2 equals 1. So when it says, excuse me, on number 2, when it says use function notation to evaluate this function for x equals 5, negative 3, and 0.5, those are not the questions that I'll ask you. The question that I will ask you is I will say find f of 5. I will say find f of negative 3. I will say find f of 0.5. Okay? And when I do that, this should trigger you right here. This letter should trigger you. Okay, I'm finding the f function. So what is the f function? 9 minus 4x, right? The f function up here is 9 minus 4x. So I'm using that function, so equals 9 minus 4. And then what is x? 5. That's this input right here, right? I plugged in 5 for x. So when I come over here, I'm going to plug in 5 for x. So parentheses 5. So I find the proper function based on the variable that, or the letter that they give me. And then I also have the specific input that I'm supposed to plug in. Now let's figure out what that is. So 4 times 5 is 20. So I have 9 minus 20. What is 9 minus 20? What is it? Negative 11, okay? So then my answer, I'm going to write f of 5. So the function f with the input of 5 gives me an output of negative 11. And that's my first answer. That's how you should always write your answer. Don't write just negative 11 down. I need to know the function of f with the input of 5 gives me the output of negative 11. That's what the purpose of function notation is, so that we can see all of that in a single line. Okay, I want you to work through f of negative 3 and f of 0.5 with your partners. Go ahead. Okay, so f of negative 3 is asking me to use the f function. So the f function is 9 minus 4x. So I have 9 minus 4, and then x, my input that they give me inside the parentheses, is negative 3. So I plug that in, and then I work it out. So negative 4 times negative 3 is a plus 12. So I have 9 plus 12, which is 21. So I have f of negative 3. So the function f with the input of negative 3 gives me an output of 21. F of 0.5, so I'm using the same function, 9 minus 4, and my input this time is 0.5. So half of negative 4 is negative 2, 9 minus 2 is 7. So the f function with the input of 0.5 gives me the output of 7. Okay, so that's function notation. Alright, so there's one more problem that I want to look at. So go ahead and flip to the next page. I want to look at 4. Okay, so 4 says, given the function f of x equals 9 minus 4x, so we're using the same function as shown above, what is the value of x in f of x equals 1? So I don't want you to do anything, but I want you to have a quick conversation with your partners, 30 seconds I'll give you, and talk about why is this problem different than all of the other problems we've done so far. Go ahead. Okay, what do you guys think? I heard some good things being said. Brandon?
Instead of finding the output, you have to find the input.
Good. Couldn't have said it better myself. Instead of finding the output, they don't give you f of a number and say find the output. This time they say, hey, the output is 1. What is the input or x value that's associated with that? So how would I set up this problem to solve it? How would I set up this problem to solve it? It tells me that 1 is what? Is 1 my input or output? 1 is my output. And I also know that this little expression right here, 9 minus 4x, should represent my output, right? So setting up this problem, I would say, well, I know that 9 minus 4x, which is my output, should be equal to what? 1. And then I solve from there. So 9 minus 4x equals 1. So I would subtract 9 from both sides. Get negative 4x equals negative 8. Divide by negative 4. And x is 2. Okay, so you have to be on the lookout for that. Usually, most of the time, they'll give you the input and you'll have to find the output. Occasionally, you will be asked a problem like this where it gives you the output. You have to go back in and find the input. Okay? All right.